Okay. All right, so I'm going to talk about mirror symmetry. So I'm going to give a bit of an introduction to mirror symmetry, which hopefully will be reasonably comprehensible, not just to all the world experts in the audience. And I'm going to introduce it with a focus on a certain idea called versality. And then in the second talk, I'm going to explain how that idea is a really useful tool to prove cases of mirror symmetry. And I'm going to show some applications of new theorems that we can prove using this idea. But let me start at the start of mirror symmetry. So string theorists, Candelas, Linke, and Shimrick, were interested in studying certain kind of threefold, Calabi-Yau threefold, that I'll get to. And they started making a bunch of examples by looking at hypersurfaces in weighted projective spaces. Weighted projective space is just a quotient of Cn by C star, but instead of the diagonal action, you act on the different factors of C to the n with different weights. And they plotted the Hodge numbers of these varieties. And to explain this picture, I'm going to draw a picture of the Hodge diamond of one of these guys. So this is a plot of the Hodge numbers of a three-dimensional variety, X. And for these particular varieties that they were considering, the only interesting ones are these ones in the central 2x2 square. And what they found was that there seemed to be this symmetry when they plotted those pairs of numbers A and B, this kind of reflection symmetry across the vertical line in this picture, which corresponds to interchanging A and B. And so this kind of suggested, maybe for each X, there's another variety X check, which we call the mirror, for which these A and B are the other way round. Right, so that's what I was just saying. When we look at these particular examples of Calabi-Yau hypersurfaces, they seem to come in mirror pairs whose Hodge diamonds are related by this flip between the numbers A and B there. So to be more specific about this phenomenon, in 1990, Green and Plesser explained a general construction that says, given one of these hypersurfaces, X, how do you specifically say what the mirror hypersurface X check is, whose Hodge numbers are related to those of X in this particular way? So they gave just an explicit construction of these kinds of spaces. And their construction was generalized by Batirev in 1994. He gave a general construction of mirror pairs of hypersurfaces in toric varieties in any dimension at all, whose Hodge numbers satisfy this mirror relationship. So now that we're not just in this special three-dimensional case, this Hodge diamond could be really big and there could be a lot of numbers in it. But these examples that Batirev constructed exhibit this symmetry where we kind of take the Hodge numbers for X and we reflect them in a 45-degree line to get the Hodge numbers for X check arising from Batarev's construction. I don't want to describe the construction in complete generality, but we will see some interesting examples a bit later. So, I mean, that was mirror symmetry turns out not to only be about three-dimensional hypersurfaces in weighted projective space or general hypersurfaces in toric varieties. It's much broader than that. And the general setting that we can study it in, or one very general setting, is for Calabi-Yau Kähler manifolds. So let me introduce that geometry to you now. So we study compact manifolds X, which come equipped with two geometric structures. So the first is a complex structure, which is an endomorphism of the tangent bundle, squaring to minus the identity, which has some integrability condition, saying that there exist local holomorphic charts so that the transition maps are biholomorphisms. And the other geometric structure is perhaps less familiar. It's a symplectic form, which means a real two form, omega, which is closed. The differential is 0. So that's kind of the analog of the integrability condition on the complex structure. And when you take it to the top power, exterior power, you should get a volume form. So an everywhere non-vanishing top degree form. And these two geometric structures are required to be compatible in the sense that this symplectic form should be of type 1,1 with respect to the complex structure. And when you put them together in the way I've indicated up there, you get a Riemannian metric called the Kähler metric. And we also require a Calabi-Yau condition. The first Chern class of the tangent bundle should vanish. So that's the geometry that we'll be studying for the rest of my talks. And mirror symmetry is about invariants of these two geometric structures. So in terminology that's inherited from physics, the symplectic invariants of X as a symplectic manifold are called the A model. And complex or algebraic invariants are referred to as the B model. And if X and X check are mirror varieties, then we expect, so I'm copying things from the slides onto the board so that as soon as they disappear, you can still remember what the idea was. So when X and X check are mirror varieties, we expect the symplectic invariants of X to be equivalent to the complex invariants of X check, and vice versa. So I'm being vague about what kind of invariance we look at and what equivalence means, because it will be different in different contexts in my talk. All right, so it's important to keep in mind that somehow there are these two arrows in the picture. but for the purpose of the talk, it will be easier just to focus on one of them. And so we'll always imagine that x, we're looking at symplectic invariants of x and complex invariants of x check. All right, but just want to refine this notion of equivalence of the invariants a little bit. By considering the parameters on which the invariants depend. So the Kähler moduli space of X, M Kähler of X, is the space of all Kähler forms on X up to equivalence. So that's the space of parameters on which the A model depends. So if we've got P in here, we get a corresponding symplectic form omega P, and we can look at invariants of X with that symplectic form omega P. So that kind of lives in a family over this Kähler moduli space. On the other hand, we have the space of complex structures on X check. And if we have a point Q in there, then we get a corresponding complex structure, J check, on X check, corresponding to Q, and we can look at invariants of that guy. And there is supposed to be an identification between these spaces of parameters, or maybe I'll make it go this way, so that our symplectic invariants of X with symplectic form omega P get matched up with the algebraic or complex invariants of X check with complex structure J psi of P. Okay? So this equivalence between these invariants is supposed to work in families in this way, and there's supposed to be an identification between the spaces of parameters on which they depend. And I just want to point out that the dimension of the space of Kähler forms, I mean, this is where Kähler forms live. They're 1-1 forms. And this is where this is the dimension of the space of complex structures. So under this mirroring of Hodge numbers, the dimension of the space of Kähler forms gets sent to the dimension of the space of complex structures. So this picture is related to that mirroring of Hodge diamonds that I mentioned before. And something that I want to mention, which is going to be relevant for the examples that I'll talk about later, is that in many cases, this identification between symplectic forms on X and complex structures on X check is mediated by a correspondence between divisors on X, well, certain divisors, I mean, not all divisors, but some finite set of divisors, and monomials on the other side that go into the defining equation of X check. So the idea is that there's some combinatorial correspondence between some divisors on X, some monomials in the defining equation of the mirror, so that if we write, sorry, maybe this is a bad place for me to be writing. I'll put it inside here. So that if we write the Kähler form on X, or rather its de Rham cohomology class, as a linear combination of these divisors, Poincare duals of these divisors, we can get some kind of parameters lambda k on this space of Kähler forms, given by the coefficients of the different divisors. Whereas on this side, if we're defining our variety x check by some equation, sum of ck times some monomial, z to the k, the vanishing locus of that, then these parameters ck give you parameters on the space of complex structures on x check. Because if you take hypersurfaces with different defining equations, they're going to end up having different complex structures on them. And this mirror map psi, at least to leading order, identifies these parameters lambda k with these parameters ck. So this correspondence between divisors and monomials is a really helpful way of seeing how the symplectic or Kähler parameters on X correspond to the complex parameters on the mirror X check. All right, so now I want to explain that in an actual example of mirror varieties, X and X check. We're going to look at a smooth degree 4 hypersurface in CP3 called the cortex surface. And we're going to look at 4 divisors on it. The divisors z1 equals 0, z2 equals 0, z3 equals 0, z4 equals 0 for each of the homogeneous coordinates zi. And we're going to look at Kähler forms where the de Rham cohomology class of the two form is a combination of the Poincare duals of those guys. Now you might notice that this is kind of a silly thing to do because all of those guys have the same, all of those divisors have the same homology class. So although we have a 4-dimensional space of parameters, they only map to a 1-dimensional subspace of the Kähler moduli space under this map here. But okay, that's fine. We're only going to look at that 1-dimensional subspace. All right, the mirror is a different variety, X check. It's going to hopefully be related to X according to this symplectic invariance of X will be equal to complex invariance of X check and so on. And we define it by taking a different quartic hypersurface in CP3 whose defining equation looks like that. So we have 4 parameters, ck, for the 4 homogeneous coordinates, x1, x2, x3, x4. We look at that quartic hypersurface, we quotient by a certain finite group action, and then we resolve the singularities. Now it turns out that even though we have a 4-dimensional space of choices of these parameters ck, up to isomorphism, we only end up constructing a 1-dimensional space of complex varieties up to isomorphism. but the mirror map identifies these one-dimensional spaces in the Kähler and complex moduli spaces in a way compatible with the identification of lambda k with ck, these 4 parameters. But there's a more interesting thing to look at, which is the other direction of mirror symmetry in this case. So rather than looking at symplectic forms on X, we're going to look at symplectic forms on X check, this variety whose construction I just described to you. And that one has a lot more divisors. In fact, there are 22 of them. So we still have, recall we took some quartic hypersurface in CP3, quotiented by a group action, and then took some resolution. So we still have 4 divisors given by the vanishing loci of the homogeneous coordinates. And under this correspondence between divisors and monomials, those divisors xi equals 0 get sent to the monomials zi to the 4th. So where do all these extra divisors come from? Well, when we quotient by this finite group action, it turns out to create some singularities. It creates 6 singularities of type A3, which lie at the intersections of these divisors xi equals 0 with xj equals 0. And when we resolve them, we create the 3 in the name A3 means when you take a minimal resolution, the point is replaced by a chain of 3 P1s. And those P1s, those little curves, will come in a chain connecting the divisor xi equals 0 to the divisor xj equals 0. And we're going to give them labels by quartic monomials, as I've shown there. All right. So now we have a 22-dimensional space of set of divisors. They turn out to map to a 19-dimensional space of Kähler forms. And similarly, we've got 22 different quartic monomials that go into the defining equation of our quartic hypersurface. And up to isomorphism, they give you a 19-dimensional family of complex varieties. And this correspondence between divisors and monomials that I've described for you here, or up there, tells you how Kähler forms on X correspond to complex structures on this quartic surface, X check. Okay, so that's a less trivial example where we see how these structures correspond to each other. So now that I've explained to you how the parameters on which our invariants depend correspond to each other, I'm going to start telling you about the invariants themselves, these A of x omega and this B of xj. So I'm going to make a kind of chart of the different kinds of invariants A and B that we consider in mirror symmetry. Yes, but if you allow yourself to act on CP3 by linear maps, you can kill the coefficients of the other monomials. So up to isomorphism, we're seeing everything. So the first kind of mirror symmetry that we look at is called enumerative. And as the name suggests, the invariants we're looking at are just numbers. And the numbers that we look at on the A model, the symplectic invariants that we look at, are called Gromov-Witten invariants. Which are defined to be counts of holomorphic maps from a Riemann surface to X with some marked points on the surface which are constrained to lie on some cycles inside X. And these counts come weighted by a factor of e to the negative area of U measured with respect to this 2-form omega. So somehow, if you can imagine, this weighting means that the curves of very, very large area count less towards our sum. So here's an example of a Gromov-Witten invariant. If we take in 3 cohomology classes on X, we can represent them as being Poincare dual to 3 cycles inside X. And the Gromov-Witten invariant associated to those 3, that takes in those 3 cycles, spits out a number which is the sum of curves, maps from P1 to X, CP1, which sends 3 marked points onto the 3 chosen cycles that are our input. So that's an example of a Gromov-Witten invariant. The B side of mirror symmetry in this version, the numbers that we consider are periods, which are integrals of holomorphic forms over cycles. So the prediction that A of x equals B of x check means curve counts on X should be equal to periods of X check. So periods are something we can compute. Curve counts are a bit more mysterious, so this is usually taken as being a prediction for these mysterious curve counts in terms of something computable. So Candela, Stella, Ossa, Green, and Parks computed the mirror predictions for curve counts on a degree 5 hypersurface in CP4 coming from mirror symmetry. And these were proved by Giventhal and Lian Liu and Yao, together with generalizations beyond the case of the quintic threefold. So we understand this version of mirror symmetry in a lot of examples. Now, the way that these invariants, these numbers kind of correspond is you put them together in a generating function and do some kind of weird, like massage it in a weird way and they come out to be the same. A more conceptual way of phrasing what this version of mirror symmetry says is using a formulation due to Morrison, which we'll call Hodge theoretic mirror symmetry. And the kinds of invariants we look at here are variations of Hodge structures. So a variation of Hodge structures over a space M is, a concept that's been studied a long time, long before mirror symmetry. So it consists of a vector bundle together with a filtration, and that should say a flat connection, nabla, which only hurts the filtration by 1. So it doesn't preserve the filtration, but it also doesn't behave completely randomly with respect to it. This final condition is called Griffiths transversality, and it will be relevant to my point a bit later. So in this case, the B side invariant has been studied for a long time. Our vector bundle over the complex moduli space is the bundle whose fibers are just the cohomology of X check. The filtration we look at is the Hodge filtration. So the filtration induced by only looking at de Rham forms of degree greater than or equal to something. And the connection is the Gauss-Manin connection, which just says if we have a family of complex structures, the cohomology is varying trivially. So we just define that to be parallel transport, the given trivialization of cohomology of X check. On the A side, it's a bit stranger. This is called the A variation of Hodge structures. And it's also got fiber the cohomology of X. The filtration is the filtration by cohomological degree. And the connection is the Dubrovin or Giventhal connection, whose connection matrix is this Gromov-Witten invariant 0,3 that I drew a picture of on a previous slide. So that's where the curve counts go in. So Hodge theoretic mirror symmetry says, well, we've got this identification psi between the Kähler moduli space of X and the complex moduli space of X check, and it says that the variations of Hodge structures living over these spaces should be isomorphic there should be an isomorphism covering this identification psi. And it's actually equivalent to the enumerative version. There's some procedure for extracting numbers from a variation of Hodge structures which recovers the enumerative version of mirror symmetry. I'll say a little bit more about that in a second. All right, and now the final version of mirror symmetry that we'll consider is called homological mirror symmetry, or HMS. And the invariants here are categories. The B side invariant of our complex manifold, is the bounded derived category of coherent sheaves. And look, I mean, you don't have to absorb the definitions of these categories, just, you'll be able to process the rest of the talks without absorbing them, just, don't worry. But let me say the definition of the Fukaya category. Its objects are certain submanifolds of X called Lagrangian submanifolds. So these are half-dimensional submanifolds on which the symplectic form omega vanishes. The morphisms are a complex vector space spanned by intersection points between Lagrangians. And the composition maps count holomorphic maps into X with boundary on Lagrangians weighted by the same factor that we saw for the Gromov-Witten invariants, e to the minus omega of u. So here's an example of a holomorphic disk U. It has boundary on these Lagrangians L0, L1, and L2. And there are 3 intersection points, P, Q, and R. And the sum of these, count of these holomorphic disks contributes to the coefficient of R in the composition of the morphism P from L0 to L1 with Q from L1 to L2. And the D out the front denotes a certain formal algebraic enlargement. So, according to our mirror symmetry prediction, homological mirror symmetry says the Fukaya category of X with a given symplectic form omega should be equivalent, the categories should be equivalent to the derived category of X check with complex structure psi of the Kähler form we were, psi of P. And we saw that the other versions of mirror symmetry were good for making predictions about these numbers, these curve counts on X. But what is homological mirror symmetry good for? Well, it's mostly been useful as a motivating principle. You kind of see that there's a certain structure on one side of mirror symmetry, and then you say, well, if mirror symmetry is true, then the same structure should exist on the other side, and then you can go look for it there. I mean, we hope ultimately that this will be, we'll have a proof of homological mirror symmetry, and it will provide some kind of bridge between symplectic and complex geometry. Like if we prove a theorem in complex geometry, we'll automatically get a theorem in symplectic geometry by mirror symmetry. Another thing that it's useful for is that it implies the previous versions of mirror symmetry. So there are implications going in this direction. And the idea for how this should work goes back to Kontsevich and Baranikov, but in joint work with Ganatra and Perutz, we managed to give a precise criterion for when this happens. But not only are there these kind of implication arrows, in some sense, homological mirror symmetry is less surprising than the other versions. And the reason has to do with versality, the idea that I said my talks will be about. So let me explain. First I had this quote from the paper where Kontsevich introduced homological mirror symmetry. He said, "Our conjecture, if it is true, will unveil the mystery of mirror symmetry. The numerical predictions mean 2 elements of an uncountable set coincide. Our homological conjecture is equivalent to coincidence in a countable set of connected components of the moduli space of triangulated categories, whatever it means." So what does he mean? I didn't read this and then, say, oh, okay, I'll go think about that. Once you have thought of the idea of versality, then you kind of go back and see, all right, that's what he was talking about. But let me tell you one version of what he's talking about. So suppose that we know how to prove mirror symmetry at one point in the moduli space for any of these versions, homological or Hodge theoretic or whatever. So we've got one point in here and one point in here, and we've matched up the invariants lying over those points. Okay. if we've matched up those invariants, whatever they are, Hodge structures or categories, it means that the space of all deformations of these invariants also match up, because they're the same thing. So what's one way of deforming the algebraic structure that we're looking at? We can deform it by deforming the geometric structure on which it depends. That means we get a map from a neighborhood of a point in the Kähler moduli space to the space of all deformations of the invariant we're associating to that point. And similarly on the complex side. And versality, we say the situation is versal when these maps are local isomorphisms. So that means that every kind of formal algebraic deformation of our structure comes from a deformation of the underlying geometric structure. All deformations are geometric. And this implies, in this situation, it implies that mirror symmetry holds at all the nearby points. We have an identification psi between these two neighborhoods, which is the composition of these three isomorphisms. And the way we've defined it, kind of almost tautologously, means that the A model over P, or P prime, corresponds to the B model over psi of P prime, where psi is this map. So this is the kind of central idea of my talks, this strategy for extending an understanding of mirror symmetry at one point in the moduli space to all the nearby points. But this strategy does not work to prove Hodge theoretic mirror symmetry. And the reason has to do with this Griffiths transversality condition that's part of the definition of a variation of Hodge structures. So a variation of Hodge structures can be classified by a period map into some period domain. And Griffiths transversality says that the differential of this map has to lie inside some horizontal distribution in the tangent space of that period domain. And it can't be a local isomorphism unless we're in dimension 1 or 2. I mean, you might imagine that maybe the image of the period map is the unique integral submanifold of this horizontal distribution if the distribution were involutive, and then you would still have some kind of uniqueness result, but even that is not true. And in fact, in some sense, it's kind of a good thing that it's not true, because the procedure whereby we extract interesting numbers from a Hodge structure is exactly consists in finding the undetermined Taylor coefficients of this period map rho. So you've got some constraint on the image of this period map. Differential has to lie inside some distribution, but that under-constrains it, so there are a whole bunch of undetermined Taylor coefficients, and those coefficients are the enumerative invariants that we study in mirror symmetry. Okay, so versality does not work for proving Hodge theoretic mirror symmetry. However, it can work in order to prove homological mirror symmetry. The map from a formal neighborhood of, forget it formal. the map from a neighborhood of P in the space of symplectic parameters, parameters on which A invariant for chi category depends. The map from that neighborhood into the space of deformations of the Fukaya category is, in a number of reasonable circumstances, a local isomorphism. So versality holds. All deformations come from geometry. And same thing on the mirror side. In a bunch of reasonable situations, all deformations of the derived category come from deforming the complex structure on X-check. And a variation on this strategy, I mean, this strategy isn't exactly the one that we'll use, but a variation on this strategy is very effective at proving homological mirror symmetry, as we'll see in the next talk. So my plan for the next talk is to start by stating a bunch of new examples of homological mirror symmetry that we can prove and what they're useful for, what applications we can get out of them, and then move on to this proving the idea that we use to prove them using this versality idea. All right, let me stop there.
I have a question. What did you exactly mean by we use the undetermined coefficients to?
That has a complicated answer. I mean, we basically prove that near I'm not sure I'm going to say this in the most transparent way, but near the kind of boundary point we look at in mirror symmetry, we prove that these variations of Hodge structures that get matched up can be put into some kind of normal form. And that's somehow about, you have some distribution and you're kind of choosing local coordinates so that the period map looks like the graph of a function, and the distribution kind of tells you certain coordinates have to be constant. And then there are some extra coordinates which live in certain degrees in cohomology, and those will be some function of the period domain, and that function is a generating function for the invariants that you look at.
More questions? Thank you again. And so we will be back at 5:30.